Start the webinar. Thank you everyone for joining. Welcome. Today's webinar is regarding the airflow valve options for critical environments. So I'm Kim Klaas, the European Marketing Manager at Controls Products at Johnson Controls, based in Brussels. Today, along with Marcello Passoni, our European Business Development Manager for Critical Environments, we are pleased to review the we actually have the opportunity to review the different airflow valves for critical environments and understand the pros and cons for each type of them. But before we start, we would like to take you through some logistics of this Zoom webinar. You are all muted. However, you will have the occasion to post any question you might have at any time during the webinar. If you check your menu bar at the bottom, you will see an icon Q&A. If you click on the icon, a pop-up window will appear on your screen and you can post your question at any time. Also, during the presentation, we'll have some poll questions. We would encourage you to answer those questions, as that will actually be our guide for focus area throughout the presentation. Also here, a pop-up will appear on your screen and it will disappear as soon as you answer the question. So by the end of this webinar, you will be able to identify the mechanical and technological differences between damper style valves, measured airflow valves, and Venturi air valves. You'll also distinguish the features and the benefits of each type. And you'll even recognize the best application for each valve type within critical environments. Johnson Controls transforms places and spaces where people live, work, learn, and play. We are in 90% of the world's most iconic buildings. With a history of 135 years of innovation, Johnson Controls delivers a blueprint for future for industries in smart buildings, cities, healthcare, schools, entertainment, transportation, and many more. With a team of 100,000 experts globally in more than 150 countries, we offer the world's largest portfolio of building technology. Johnson Controls has many brands to be very proud of. Today in this webinar, we'll focus on the Triatec product with his airflow valve options for critical environments. I will now hand over to Marcello Passoni, our expert, who will share his great knowledge.
Thank you, Kim. And good morning, everyone. So first of all, I really like to thank each of you for taking time out of your busy day to attend this webinar. We really hope that really this session will be very helpful for all of you, as Kim already said, to learn the different type of valves for critical spaces, to really deep dive into the VAV boxes, deep dive into measure airflow valve overview, and as well as Venturi air valves. Of course, there will be some session to review all the slides, all the information that we're going to share in a few minutes. And at the end of the webinar, we have some time for question and answering. Just be aware, in case of time restrictions, we'll get back to you after the webinar with all the answer to your open questions. With that said, let's go through the application first. So we mentioned that we design air valves for critical environment spaces. What those spaces are, first of all. So in those spaces, there is one principle which is common across all of them, which is safety. Safety comes first. It's the pinnacle for staff members, for patients. There is nothing more important than safety. And you will see this word being repeated many times during the webinar, because that's going to be really the critical factor to address critical environment spaces. And at Johnson Controls, we commit to improve life when things matter. So we divided the critical environments in three main trunks. Starting from the left, you can see the healthcare market, operating suites, isolation rooms, clean rooms, emergency rooms, oncology suites, and burn units. So nothing more actual than that, right? In the middle, we have the pharma, indoor growing facilities, government facilities, K-12 and university labs, biocontaminant facilities, and so on. And on the right, we also have some verticals related to the pharma, but it's very niche or very specific one, like vivariums, like wet chemistry labs, food research labs, crime labs, mortuary labs. So all of those are critical spaces that we want to serve with our technologies. And again, all those different spaces are linked by one specific word, which is safety. So the laboratory control objectives is to capture fume hoods or to capture contaminants from fume hoods, as well as to keep laboratory with the right pressurization in place. And of course, because people work every day inside of the labs, also we need to enhance comfort over there. And of course, also we want to have the possibility for local and remote monitoring about all the parameters within this lab. This infographic shows how a chemistry lab looks like. So as you can see, we have air valve for supply and exhaust, but as well we have air valve along with fume hoods. So the fume hoods is critical in the laboratory because it can, as I said before, contain contaminants within the space, avoiding that people can be infected by any contaminants. But as well, it's important to keep pressure within the lab negative in order to avoid that everything can escape from the lab and go into a common space where people can work without protection and so on and so forth. So pressurization is critical, as well as critical is the containment of chemical agents within the fume hoods. And that's the reason why airflow valves are extremely important to maintain conditions safely within these spaces. So the pinnacle in laboratories, as I said before, is safety. So researcher safety is top priorities. And therefore, we need fast and dynamic solutions that can really react upon condition changes within the space. Also, it's critical in those spaces to keep research and production integral. So you can imagine the amount of money and investment those companies does to create new drugs and so on and so forth. So conditions are critical, otherwise experiments cannot be approved. Healthcare objective is slightly different than healthcare, although, as I said before, they are linked with a single word, which is safety. And of course, now in the healthcare business, so the main target is about operational flexibility, you can see here. So we have patient's room that can be converted easily from isolation to standard patient's room. As well, we need to make sure that our operating suites or operating rooms are pressurized accordingly to avoid infections of people that are currently under surgery. So this infographic shows how an operating suite looks like. You can see that we have air valve to supply, air valve for the exhaust. In this specific case, the pressure should be positive. So we should not get anything get in, because you can imagine that we might have a patient on the bed. So no infections are allowed. So pressurizing the space higher than outside on the anteroom or corridor to avoid that any infection can't get in. But differently, for instance, when you look at isolation room, it works on a different principle. So we need to take the isolation room negative, because in those isolation rooms, we might have patients with COVID-19, right? So we should not get anything getting out from these rooms. So, I mean, the flexibility of our system, of critical environment system, should really allow this type of approach. So to change the space depending on what type of situations you might need to address. And of course, in the healthcare business, we have different type of spaces like isolation room, as I said before, surgical suites. We have also pharmacies and patients rooms. So the healthcare business might be very fragmented in terms of applications. So we might have different set of applications within the same building. So that's the reason why really we need to provide solutions that are very flexible and can be adjusted and adapted based on their requirements. So when we talk about airflow control devices, we can basically classify those in two main families. So the first one is called mechanical pressure dependent valve. And the second one is mechanical pressure independent valve. That really is a big difference between the two families. It's not just the IN, which is the difference, it's more than that. It's about the operational principle, it's about the benefit that the different technology can bring. And that's really the scope of today, to deep dive into those different technologies to understand the operational principles and to see really which type of technology might be used in those critical environment spaces. So when we talk about mechanical pressure dependent valve, it's obvious. It means that we are dependent by the pressure, and everybody knows that if you raise the pressure within the duct, I also raise the airflow. So it's pressure independent. And we call those closed loop valve. It means that those valves react directly against the variation of the measurement flow, in this case, airflow. So we directly measure the airflow through different type of technologies, and we adjust the position of the blade to provide the right amount of airflow within the spaces accordingly with what we have seen before. While the mechanical pressure independent valve is not directly related to the pressure or to the airflow. So it's independent by those factors. They don't have any sensor to measure airflow, to measure a differential pressure, to measure anything of those parameters. We just need to detect the position of the valve to understand what's going to be the flow rate through it. So it's a complete different technology. From design standpoint, a little bit more complex. From ultimately, it can provide great features because it's pressure independent. So regardless the static pressure changes within your ductwork, your duct system, there is no implication on the output of the airflow in the spaces. And by knowing what we have said before, that we need to keep spaces always controlled, always pressurized, positively or negatively. So having a pressure independent solution is extremely high benefit, because regardless the static pressure changes, we can keep the airflow constant, and we can ensure those spaces are properly controlled and pressurized. So that's the first poll question I'd like to raise to all of you. So which airflow control devices you work with the most? So we give you some seconds to answer to this question. Please check the box. And after a few seconds, we can expose the result, just to understand how the audience is actually consists by. So it's which type of technology you have used the most in the past, you are familiar with. And again, I'm not telling that one is better than the other. I'm just explaining the differences between those and to see which one is the best option for critical environment spaces. Each technology has pros and cons, but really depends about the application you want to serve to identify which is the right one. So I'm really glad to see that the majority of the people in this call has experience with VAV boxes. And that's fair because it's a sorry. And that's fair because the VAV technology is well known in the market since more than 40 years. So that's something that everybody's familiar with. But before going through the deep dive about the technologies, let's really see what might be the factors that might affect the airflow accuracy in those spaces. So we said already, critical environment spaces require safety first and require accuracy, high speed of response. Because if you want to enable safety at any condition, we need to react first. And when we react, we need to be accurate in the reaction. So let's really see what type of factors might affect the flow accuracy. So first of all, installation issues. We have balancing. Speed of response is critical as well. The stability across the different changes in the building conditions, accuracy, and maintenance. So those are, I think I put those 6 as the top factors that might affect the airflow accuracy within critical spaces. So installation issues require some specific installations constraints. So you need to install your valve at specific distance from elbows or from the fan. Field calibration, it requires adjustments periodically. Speed of response, sometimes it might be too late to act. So let's really see how those technology can address all those points. Pressure variation, how those technology react to any pressure variation. And of course, when we talk about accuracy, let's see what's going to look like as concerning control characteristic, each of those valves. And of course, maintenance, last but not least, you guys know those are critical spaces. So unplanned downtime would not be really accepted by the facility manager, by the customer. Again, don't forget, we serve critical spaces. So also the maintenance is extremely important to be carried on, let me say, with some specific schedule. So you cannot allow unplanned downtime on those spaces. So when we talk about installation issues, so there are some recommendations from ASHRAE. I think everybody's familiar with. So when we install VAV boxes, we need to install those in a specific position within the duct stream. So we need to stay 7.5 diameters away and 3 diameters before to avoid really for a proper installation. Otherwise, we might have wrong reading of the pitot or the flow sensor, and that wrong reading might affect the operational of the VAV boxes. As well as we might have balancing and calibration conditions. So we might have changes in the pressure velocity, and those changes might affect, again, the reading. And since the VAV are closed loop, they react again pressure reading, as I said before. So we need to put K factor to adjust those different conditions, but we can only set 1 K factor. We cannot go with more than 1 K factor. And that sometimes could be a limitation in these spaces because we cannot carry on the entire operating range. So we just put 1 K factor as a correction factor, but that's not probably allowed to maintain the same accuracy across all the operating range. And you guys know that especially the sensor are the one that can add inaccuracy within the control loop, because each sensor has an accuracy full scale. But when we change the operating range, this accuracy might be even higher than what is declared as accuracy full scale. So again, it's critical when we have devices that measure airflow to keep operating properly across the entire operating range. As well, we have speed of response and stability. So that's another critical factor. We said before, we need to react fast. If you want to deliver safety, we cannot wait. Simple like that. Because all our closed loop solutions react directly to a variation of the air or pressure in the system, you can see that we might have some latencies because we we always need to have a controller. We always need to have some brain, some unit that elaborates the input coming from the sensor, and basically doing the algorithm tell to the blade where to position. So it's basically acting against air or pressure variation. So, and this action, this loop, it might have 2 to 3 seconds inherent delay. So that's critical, as I've said before, because we need to act quickly, we need to act immediately. And also, one of the limitations of this technology, I would say, when we look about speed and response stability, is the fact that there is a variation, a drastic variation on pressure or flow rate. It takes a while before going to the right set point. Again, it's a continuous loop of controls. And you will probably see the actuator moving so fast and so often, always to hunting the right position to deliver the right amount of airflow in those spaces. Again, it's a reliable technologies everybody's familiar with. I just want to highlight some of those limitations that this technology might have, as well as the maintenance. So those are real pictures out of real installations that we have carried on. You can see that we might have sensors that are completely blocked by the breathes. They're completely stuck. And by having sensor that doesn't read properly, I'm pretty sure that even the output would not be the right one. So that's extremely critical. But also when we look at the laboratories, we have find those type of situations every now and then. So where the sensor were stuck by chutes that were sucked by the exhausted fume hoods air valve. So in this type of condition, you don't read anything. So basically you will keep your blade full open regardless the real condition in the space. So by having a condition like that, the control is lost. You don't know what you're doing. You don't know what you're controlling. Simple like that. And of course, you need to carry on maintenance. And that's extremely important because it drives cost to the operations. You have to stop tests. You have to stop surgeries to make cleaning of those stuff. And even more critical, you always need to remove the valve from the duct to make cleaning. Otherwise, there is no possibility to access to the valve and remove those stuff from inside without removing the valve from the duct. So that's another consideration we have to take in mind. So when we talk about damper style VAV boxes, I think that's really, it's a technology that is, as I said before, it's in the market since more than 3 decades, right? So it's variable air volume. VAV is a type of HVAC system. So differently from the constant air volume that supply constant airflow at variable temperature, VAV systems vary the airflow at a constant temperature. So the advantages of VAV systems over constant volume system include more precise temperature control, reduced compressor wear, lower energy consumption by system fans, less fan noise, and additional passive dehumidification. It's used to control zones for occupant comfort. And so if you are in a restaurant and it seems to be hot or cold, you can just ask to turn the temperature down or up to adjust the comfort. It's a pressure independent solution. So if pressure changes within the ductworks, the blade will react accordingly. So we'll change the position to deliver the right amount of airflow. They typically use standard speed, but actually they are also available with fast speed actuator. But you will see later on, because of the control capabilities of the VAV, it's really hard to use fast speed actuators because it's really hard to control due to the nature of the control characteristic, due to the nature of the control type of the VAV boxes. Again, it's very simple. We have an airflow going through the sensor. So all the sensors are exposed to the airflow stream. So the sensor reads the pressure velocity. It sends the signal to the controller. The controller has an algorithm inside that, based on the reading, based on the set point, will adjust the blade position. So it's a well-known technology in the marketplace. It's very, let me say, it's very cheap, I would say, really. So it's not expensive at all. It can provide great airflows in terms of really amount of meter cubic per hour airflow. But I do see this technology really the best technology for non-critical spaces for all the reasons I explained before. So if you want really to deep dive about the control characteristic of the VV boxes, you can see how it works. It's basically a kind of on-off solution. So it's very difficult to control, especially at the beginning of the opening, at the end of the opening. So in those two range, in those two positions, it's almost impossible to control the flow through the duct. That's the reason why the VAV are often classified as quick opening or on-off devices. So they have a rangeability or turn down ratio is the capability to control the flow of 3-to-1. It's basically, as I said before, it's a quick opening. You cannot allow many points of controls to all the rotation of the blade. And that's one of the limitations we have when we talk about control characteristic, when we talk about accuracy. But also we have seen that the VAV also has some other limitation, I would say. One of those is the time delay. So time delay, or it's called also signal latency, between the airflow sensor in the VAV boxes. So it's critical. Sometimes it takes seconds before going to the right position. And it's always hunting the right position. So you will see the blade moving many times during the day. And that brings another issue that the actuator life could be reduced because the actuator is asked to play many times during the day. And their lifetime could be shortened because of that, which means that you need to carry on replacement more often than other type of technologies. We will see later on. As well as we said before, so the flow sensor is exposed to the airflow and can easily become blocked. So this condition requires maintenance. But first of all, this condition provides unclarity about what you are controlling because the measurement is not appropriate or is not correct. So also we have strict guidelines and protocol for cleaning inside critical spaces. So as I said before, we cannot interfere with daily use of healthcare or laboratory or surgery room. And of course, it must be cleaned much more often than other type of technologies. So cost of maintenance is going to be much higher than other type of technology we'll see today. We have a very low turn down ratio. Turn down ratio is basically the rangeability, is the capacity to control airflow in those spaces. It's pretty low. And low speed of response. So again, because we have some latency, because we use standard speed actuator, and of course, in some cases, even high speed actuator, but high speed actuator go against the low turn down ratio. Because again, it's already an on-off solution. So if you go with fast actuator, you lose the control completely. And so those are some of the limitations that the VAV brings it. The technology used in the VAV can have. So we have to consider those when we install VAV boxes in critical spaces. I'm not saying that VAV boxes cannot be installed in healthcare facilities or in laboratories facilities. They can be installed over there, but not in critical spaces. So I would install VAV boxes on waiting rooms if I'm in the hospitals or I will install VAV boxes in cafeterias if I'm in the hospital. As well, VAV boxes installed in the pharmaceutical companies in spaces where are not critical. But when it's about critical spaces, when it's about safety, when it's about accuracy in control, when it's about speed of response, VAV doesn't answer all those questions. And regardless of the fact that this technology is well known and well used in the industry, regardless of the fact that this technology is price competitive, it's simply not the best technology for those critical spaces. And again, just want to remind again, the risk to get those sensors being blocked, it's too high. And if you have those sensors failing, the entire airflow control system is failing. We also have measure airflow valves, which looks like the VAV boxes for some degrees. So those are closed loop valves. They measure variables and they react against those changes. We have many ways to measure airflow. We can measure the differential pressure. We can measure vortex sensors. We can use different type of sensor to measure airflow. It's still pressure independent. So in case of pressure changes, there is a direct implication on the airflow as well. It's also used fast or standard speed actuator. And it's like the VAV boxes use damper blade style. But also in this case, the damper blade might vary model from model, model to model. You can see here on this picture, the EcoAir valve solution by Johnson Controls. They have a patented features around the blade. You can see those black fingers around the blades have been introduced to improve the turn down ratio, to improve the rangeability, to enable more control at the opening, the closure of the valve. So again, the turn down ratio might be different depending on the blade design. We might have different type of materials available. It could be stainless steel, it could be aluminum. We might have solutions with insulation to avoid condensation. One of the, let me say, pro of the VAV boxes and the measure airflow valve is that they can both operate with a very low differential pressure. So you don't require a certain differential pressures to make your system working properly. So they can really start working with a very low differential pressure. And that's extremely important because really you can, in some cases, you might have valve installed far away from the handling units, from the fan, but since they don't require a minimum differential pressures to operate, they can work properly, regardless where they are installed. So those are some of the pros also that we have to take into account when we look at the measure airflow valve as well as the VAV boxes. And because of the design concept, they can bring a lot of airflow through the valve, through the space. While you can see there is a blade, when the blade is fully open, there is no obstruction to the flow. So you can really carry on as much as you can on, as much as possible, the flow through the duct. And of course, the flow might vary depending on the valve size. But of course, because of the design, of the mechanical design of the valve, those can enable you to bring a lot of meter cubic per hour of airflow in those spaces. And in fact, you can see here that compared to the Venturi valve that you will see later on, we have much more capabilities in terms of flow rate. And of course, the VAV boxes and the measure airflow valves do not require any specific orientation. So we said before that you need to install the valve at some specific distances from elbows or from the fan or from the handling units, although the orientation, so vertical, horizontal, is not critical for those valves. While you will see this probably critical for Venturi valve. But let's wait a while before going through the Venturi valve. So here is really how the valve works. So basically we measure, in this case, the differential pressure across two accurate diameters. And then there is an algorithm inside of the controller that based on the differential pressure, it can provide it can tell the actuators where to position the blade. Again, it's still a pressure dependent, so we react against pressure changes in this case, differential pressure changes. It's due to the black fingers that you can see here, we can have a much greater control capabilities compared to conventional VAVs. It's also important to say that those type of measure airflow valves typically, I would say typically, because we know that in the market there are some type of valves that use the same principle, that they have sensor exposed to the airflow, but in the majority of the cases, the sensor is not exposed to the airflow. So here there is a less risk of contamination of those sensors, less risk to get these sensors being blocked because it's not directly exposed to the airflow. So the risk to get this sensor not operating is very limited. Although because we still have a sensor, we might have this risk in place. So it's more expensive than a VV boxes because it's more precise, first of all. So we have high precise sensors within our eco air valve to maintain the accuracy across the entire operating range of the valve within plus minus 5%. It's still measuring variation, in this case of differential pressure, to adjust the airflow. So we might have some latencies in the response. We may also have potential sensor drift across the lifetime of the valve. That's natural. That's, of course, it's due to the fact that we have sensors, and those sensors might adjust some recalibration over time. Those sensors might have drift over time. That's because of the sensor. It's not because of the type of valve. It's pressure independent still. So just bear in mind that if you have a pressure variation in your system, the blade will start reacting. So it's basically is a reacting system. So for any pressure variation, the blade will move position. So which also brings some critical around lifetime of the actuator. So the actuator might be replaced earlier than within other technologies. So the airflow might be measured in different ways. So as I said before, as a Johnson control, we use the differential pressure measurements to determine the airflow to the valve and then adjust the blade accordingly. We have the black fingers, don't forget it, to increase, which is a patented feature by Johnson, to increase the rangeability, so the turn down ratio. And as I said before, the measured air valve as well as the VAV and inlet sensitive. So regardless where you install the valve in any position, it doesn't bring any critical or criticalities within the measurement of the valve itself. So just to summarize, in short, some of the key points of the measure airflow valve, the eco air valve from Johnson, is a very ultra low duct static operating pressure. So as I said before, we don't need a minimum differential pressures to operate. We could say maintenance-free design because the sensors are not exposed to the airflow. So in a remote case, you might get those sensors being blocked. You don't also need to remove the valve from the duct. You just need to blow some fresh air from those two ports. So again, also from maintenance standpoint, in the remote case, you have those sensors blocked, the time of maintenance is reduced because you don't need to remove the valve from the duct. So no straight duct requirements. Also in this case, we have, according to the ASHRAE you have seen before, we can install those valves even close to the elbow or even close to the fan because we measure the delta P. We don't measure the airflow, we measure the delta P. So we also have less installation constraints compared to conventional VAV boxes. We have turn down ratio 8:1. We have no installation constraints about the orientation of the valve, so it could be installed in any direction you want. No clean out maintenance door, so we have no, you don't need to open the valve, you don't need to access to the sensor. As I said before, you just need to blow fresh air from those two pins and the sensor are fully operating as the day one. Other technologies that use vortex sensor that sometimes is exposed to the airflow require some opening to get access to those sensors to make some cleaning or some adjustments over time. We can bring a lot of airflow in terms of meter cube per hour on the same duct diameter, so then you can optimize your design by using smaller sizes, so you can reduce the cost of the overall building by using smaller diameters. We can also provide ganged solutions, so more than one valve mounted together in a single rack when the request of flow rate is really higher. And as I said before, we use the differential pressure, so we electronically simulate a pressure independent solutions. So to keep flow constant regardless the static pressure variation. So that's important. So by touching this point about the pressure independencies, it allows me to go on the Venturi valve. And basically, based on the answers that you already provide on the first poll question, I think no one of you is actually familiar with Venturi valve. But please let me know if you heard about that, if you know the operational principle of a Venturi valve, if you probably just heard some rumor in the industry about the Venturi valve, how do they work, what's the benefit of those, that would be very important for me. And again, here you can see now, from now on, a complete different technology that basically address the same requirements on critical spaces. But we basically move from a pressure-dependent solution. And again, you have seen the relationship between variation of the pressure or variation of the pressure velocity or the variation of the air and the adjustments of the blade. So it's a continuous closed loop control system to a pressure independent solution. So which it works in a completely different way. So a Venturi valve, first of all, what is a Venturi valve? Venturi valve is a valve that is independent by the static pressure. You can see the design is completely different than what we have seen so far, VAV boxes and eco air valve or measure airflow valve. Is a highly actuated flow metering devices with Venturi shape. The first difference between Venturi valve and VAV boxes and measure airflow valve is that we don't have any sensor. We don't read any differential pressures. We don't read any airflow. We don't read any pressure velocity. We don't read anything. The only thing we need to read is the position of the valve. We, in this case, but any Venturi valve use a dynamic cone and spring assembly for pressure independence. And you will see in the following slides some animation about how this cone operates. The valves are designed to provide plus minus 5% accuracy across the entire operating range. And we can provide Venturi valve with standard or fast-acting actuator option. Again, some specific applications require fast-acting, so actuator that should act within 3 seconds. Some other don't require fast-acting, so we have both options to meet any potential customer needs. So here you can see how the operational principle looks like. So if you want to increase or reduce the airflow within the space, you just need to change the signal on the actuator and change the position of the cone within the valve. So as I said before, we don't have any measuring devices, but of course we have a potentiometer, and within our technology we use a effect hole sensor to determine the position of the valve. That's critical. Okay, and that's also the reason why we get rid of conventional potentiometer and we use this type of technology, which might result to be more expensive, but ultimately It will provide high reliability, no drift over time, accuracy across life. And so we decided to abandon conventional potentiometer technology and use sensor effect hole to really make sure that our technology is premium and to ensure that our products are reliable across the entire life of operation. And so this potentiometer or this sensor effect hole will provide an output confirming the position of the valve. And by knowing the position, we know what's going to be the flow rate because each valve is factory calibrated. So we know exactly based on the valve size, based on the calibration being made at factory level, if you are at 50% of the stroke, what's going to be the 50% in terms of airflow. But we don't have measuring devices in between. Again, if you want to increase the flow rate, so if you want to increase the meter cubic per hour capabilities, we just need to act on the actuator and the change its position to allow more air or less air to get in. But of course, we know that pressure might change within the system. And what happens? So if the pressure change, the actuator remain fixed on the last position and the spring within the cone will move to adjust or to release, to absorb or to release the pressure changes. So regardless, the static pressure changes, the airflow will not be impacted by that. So the airflow will remain stable regardless the static pressure changes. That's a phenomenal result. That's a phenomenal achievement, right? Because we might have those condition changes in the spaces, but again, the airflow will remain stable. That's impressive. So we don't keep the actuator running to, let me say, hit or to hunt the right position. And each valve is factory tested on 49 points. It is tested according with NIST certification. The Venturi valve, due to the design, you have seen we have a cone, we have a lever where the cone moves on, can provide a really higher turn-down ratio than any other airflow valve in the market. And actually we can achieve 20-to-1 turn-down ratio. That's really quite impressive. So you remember the VV was 3-to-1, the measured airflow was 8-to-1. With the Venturi valve, we can go 20-to-1. It's really impressive. Of course, we have some pros, but also we have some cons, and I'm very open to share those. So we cannot compare Venturi valve with any VAV boxes. It's a completely different technology. So anytime you put VAV and Venturi valve, make sure that you are really comparing apple to apple, and that's not the case. So cost is much higher because the design and the construction of the Venturi valve is completely different than VAV boxes. It requires a minimum differential pressures to operate. So the cone, we have said before, inside of the cone there is a spring. And to enable the spring to operate correctly, we need a minimum differential pressure to make this spring working properly, which is not an issue in all the buildings we have played with or we install our valves. Sometimes it's not an issue. It might be an issue where you have valves really far away from the air handling units, far away from the fan. Then where probably you might have some issue to install the Venturi valve. But again, the important point, and you will see later on, is that you can use the two technologies together. So one does not exclude the other. So that's important also to say. Specific to valve orientation, yes. So since all the valves are factory calibrated, we need to make sure that we calibrate the valve based on the installation orientation type, because the gravity might have an impact on the cone, on the spring, right? So we need to take this into account when we calibrate at factory those valves. So it's specific to valve orientation. So we need to know upfront if the valve will be installed horizontally or vertically, because those Venturi valve requires those information for being calibrated. So we can also, in order to ensure that the valve is working properly, the valve is available with 2 pressure ports to measure the differential pressure across the valve. So if the differential pressure is below a threshold, a certain value, we can notify through an alarm that the valve is not working within the right conditions. That's an option. And due to the design construction type, compared to the measure airflow valve and compared to the V boxes, we typically are not able to supply the same amount of airflow at the same sides. So that's due to the fact that the cone is actually obstructing all the airflow through the valve. We don't have the full diameter open to get airflow going through it. So that's one of the limitations, although we have a complete line of valves. So we have a ganget valve, we have a single valve, we have from the N200 up to the N350 to really cover even any request of flow rate. We have also have possibility to deliver 6 Venturi valve on a single rack. Again, airflow could be a limitation, but we have solutions in place to allow to deliver the right amount of airflow based on the specification we get from our customer. It's pressure independent. That's for me is the main takeaway you have to take. So this technology is pressure independent. So the airflow remains constant regardless the static pressure changes. And that might bring great saving in terms of energy saving because we can optimize the handling unit's operation as well. And also we use fast speed of response actuator, but also the cone can react within less than 1 second. So if a static pressure changes, I immediately adjust the position of the cone to do not affect the airflow in my spaces. And by recalling what we have said at the beginning, so safety first, accuracy, stability, no maintenance. So the Venturi valve really answers to all those questions. Simple like that. Of course, there are some limitations like the differential pressure. We need to have a minimum differential pressures to make those valves operating properly. But again, as I said before, and it helps me to go on the next topic. So you can see here the design difference between the 2 valves. So that's basically summarize what we have seen so far. So the different design, different technology, pro and cons of each of those, no matter what. But important to say, high control capabilities on Venturi valve, while limited control capability on blade damper, 3-to-1, 20-to-1, that's another takeaway you have to consider. But important point here is that we can use the technology, we can combine the technology in the spaces. You can see here one infographics about potential application where you can use eco air valve or measure airflow valve, you can use Venturi valve, and you can also use VAV boxes. So again, that's a great example of using the 3 technologies in the space, but use the 3 technology appropriately, right? Again, also here, that's another infographics that shows that VAV boxes can be installed in spaces that are not critical, but then I will use Venturi air valve or measure airflow valves in spaces that require some specific control capabilities. And also by following what we have said before, by knowing that the Venturi valve requires some minimum differential pressures and they cannot work with low static pressure, you can also combine the measure airflow valve, in this case eco air valve, and Venturi valve in the same building by installing those in different floors or in different positions accordingly to the duct static pressure. So that's an opportunity for all of us. That's an opportunity to use the right technology in those critical spaces. And so if I want to summarize what we have seen before and highlight for those technologies what might be critical for our customer, you can see here really an overview of what each technology can provide. And so if you have customers that really are interested in maintenance-free devices, I think Venturi valve should be the option. But if you have customers that are really struggling about having valves that can operate with ultra-low pressure operations, then Venturi valve is not an option. So we should look at measure airflow valve or as well as VAV. But then the question will be, well, do you need better control? Yes, okay, then we can use the measure airflow valve. And remember, for critical spaces, accuracy is important. And so that's the reason why airflow or measure airflow valve should be chosen instead of conventional DAVs. And so if you want to hear from me, one suggestion, I would probably use Venturi Valve in all the full moods application due to the fact that they are fast acting, they are not related to the static pressure changes, they react very fast. So you can know the full moods might have a different conditions, so you can open and close the sash, you might have people walking through it, people standing in front of the full mood, so the conditions within the full moods might be really varying during the day so often. So by having a Venturi valve on the top of the full moods with all the coatings to resist, to withstand all the chemical agents, or all the chemical compounds, Venturi valve is the best option. Then when it's about pressurizing the space, so supply and exhaust air within the space, you can use Venturi valve if you have adequate static pressure or adequate differential pressure, or as well you can combine the Venturi valve with the measure airflow valve, the eco air valve. And ultimately, you might have used the VAV boxes for spaces that are not critical. So with that said, we basically ended up our webinar. So we give, unfortunately, 2 minutes only for Q&A. I'm sorry for that. I don't know if there is any question already in the chat.
No problem at all, Marcello. Thank you for sharing your very good knowledge. At this moment, we have no question yet in the Q&A. I do encourage you to post your question. Even if we won't have a lot of time to spend on it, we'll definitely get back to you with answers.
Right, correct. So yeah, that's important for me. So if something was not clear explained, or you still have some concern or some doubts about those type of technologies, and you want to have a deep dive, which is not going to be 1 hour. Sorry for you, it's going to be probably 3 to 4 hours. So you need to be ready for. But I'm more than willing really to set up a meetings individually with each of you and explain in details all the characteristics of those valves. We typically squeeze in 1 hour, what typically cover in 4 to 5 hours. But you know, for the benefit of this conversation, for me, it was really important to highlight the different technologies and really understand which type of technology we should use where. So that's for me, it was the most important point on this webinar. But really, I'm more than welcome to take any offsite conversation individually with each of you and spend time to look at your projects, look at your opportunities, and see if you are able to serve you with the right technology, enable you to win projects and be successful in the market. So before closing the call, we would like really to ask you to rate this webinar. So feel free to really express your overall experience with this webinar. And if you get any question, we'll be back to you within 1 or 2 days with all our answers. With that said, I really would like to thank each of you for dedicating your time to us today. Thank you so much. Enjoy the rest of the day and stay safe.
Thank you, everyone. Wish you a very nice day.